we're going to talk today about this paper, Visualizing the Loss Landscape of Neural Networks. This paper came about 2 years ago, and I like this paper very much. It has a lot of citations. If you go and look in arXiv, you'll be surprised that, perhaps not surprised. It is really a good paper. It has gotten a lot of citations, and it serves or sort of helps in one important thing. See, in neural networks, we have a lot of things we do, like batch normalization, like regularization, L2, L1 regularization, or weight decays. And so as we do all of these techniques, and then there is a concept called dropouts or skip connections, which I haven't yet explained to you guys, but think of them as a short circuit where signal can go from the earlier layers to much later layers. Just short circuit. In other words, instead of going to the next layer, some of it also short circuits to many layers later. So those are called skip connections or short circuits or residuals. And all of these tricks, each one of these tricks, when it came about, it led to an improvement in performance of the neural net. Then there is always a bit of a debate of which is helping you more. What should you be doing and what should you not be doing? So can we quantify what does batch normalization actually do? Right? Why is it leading to better results? We can give justification theoretically and say that, see, you're recentering the data, the input data, and making sure it's small enough when it goes into it. Weight decay also is essentially like regularization, L2 regularization. You're basically saying that put a constrained surface around the origin and make sure that the weights don't increase too much. Right? So every time you make a gradient descent step, if you have the regularization term, you'll notice that what it does is it subtracts the learning rate times the gradient, but it also diminishes the weight a little bit, scales it down a little bit before it takes the gradient descent step. So those are weight decays, essentially. So all of these things work. Batch size matters. I mentioned that we do not do batch gradient descent. When you take the entire data as one big batch gradient descent, you're much less likely to have good solutions. It is far better to have smaller batches, mini batches, and then the smaller mini batches, what they will do, and the intuition I gave you is, they lead to the perturbation of the loss surface from batch to batch, from step to step, right? Or iteration to iteration. And those perturbations smooth out the loss function. Right? So all of these intuitions, they become very real when we could possibly visualize it. The problem is, how do you visualize a surface that exists in something like 100 million dimension space? Very hard to visualize. Our visualization ability fails beyond 3 dimensions. Right? Maybe add color or something and get some sense in the 4th dimension, but certainly it doesn't expand out to the enormously high dimensional spaces that we encounter in neural networks. The other problem that we have with neural networks is, we know that the loss function, right off the bat we know, are not convex surfaces. That was the reason people used to not like neural networks. Right? So for the longest time, neural networks were sort of went through a winter, uh, arising from the realization that its loss surfaces are not convex, and so it's hard to converge, and it generally was practically hard to converge in neural networks. You would converge to some bad minima, local minima, and people did for many years struggled with that. They tried all sorts of things and were getting nowhere, and then came these new ideas, starting with Geoffrey Hinton and many other people, Lee Cohen and Bengio and so forth. So you can literally see that the subject has gone through a renaissance. And these ideas are, and I'll just mention some of the ideas: batch normalizations, is weight decay, then mini batch gradient descent, right? And momentum-based optimizers, and so on and so forth. Each of them contributes something to the theory of neural networks and has moved the needle forward. But if only we could see what it all means. what it all does.
Asif,
Now, yeah,
one quick question to get a little context clear in my mind, right? I missed your ML 200, right? I'm doing the ML 400, which is focusing on the deep learning side of it. So
yeah,
when we use the word neural network and try to appreciate that for its complexity, would you distinguish between neural networks that were there before the word deep learning got coined versus the ones that we're talking about today? Specifically with reference to when you use the word that they have millions of parameters. I'm trying to understand like neural networks that would have been written, let's say, to predict, let's say, a bond pricing or something there in the financial markets versus what we're now using to recognize images or to do autonomous driving. Would you
yes.
put these as two different things or would you blend them together?
Well, see, what used to exist are kindergarten or toy versions of what we have today. The fundamental distinction is that we did not have something called representation learning. The word deep learning is a buzzword that stands for something called representation learning. And these very deep neural networks allow us to do representation learning. What representation learning is, we will see actually tomorrow as we make progress. So roughly speaking, what it means is that when you try to solve a problem, let's say that you have data and you're trying to predict whether it's a cat or a dog, or cat or a truck, don't try to have a single model that solves the entire classification problem. But what you do is you give each layer a small responsibility. Let's say detect some geometric primitives. Is that geometric primitive there or not? And little nodes in the layers or the so-called filters, as we will learn, filters, their job is to detect something. Right? They are like stencils cut out on a page. So if the stencil is like a X, you just take the stencil all over the text, and if it matches an X, you say, okay, I found an X. So they all do small, very primitive things in the early layers, and then the subsequent layers, they combine those to generate what are called higher orders of abstraction, right? And then again higher orders of abstraction or representation. And so as you go down the deep neural network, each layer is actually doing very simple learning, right? Uh, but these little bits of learning, they accumulate. And the last layer is able to tell the difference between a cat and a dog or a cat and a truck. So representation learning theory started with, I would say that the year was 2006, and with the works of Geoffrey Hinton. But it doesn't mean that some of the architectures we are seeing today didn't exist. For example, so while it roughly is true that the neural network theory was rather primitive at that moment, and people were trying with dense neural nets and so forth, hidden networks, and they were struggling. People were hand tuning. What was happening is that they were hand tuning, but they couldn't justify why it works. A lot of hand tuning would make it work. So, for example, translation, language translation, people, you must be remembering things like Dragon naturally speaking and so forth, long, long ago. They were trying to do that. So behind them were neural networks and support vector machines. The neural networks were often hand created with multiple layers, and people were struggling to have a coherent theory of how they were creating it. All they knew is that if they kept at it, they would eventually create an architecture that somehow works. Then there was work that was done on cat's brain. How does a cat see a picture? So by actually studying the biology of cat's brain, people realize that the way it sees the brain is a very interesting way, and that is the way we'll learn about tomorrow, convolutions. That it's a very local effect. The certain regions of the brain are looking at only certain part of the image, not the whole of the image, and it's responding to certain regions. And that led to the development of the idea of the convolutional neural net. The convolutional neural net for image processing was the work of Lee Kuhn et al. And they created the first architecture, LeNet. LeNet is the classic architecture. I would say that is the hello world of convolutional neural nets that we'll study tomorrow. Was it effective? It was tremendously effective. And let me give you a sense of how effective it was. See, have you Do you remember that when we came, at least when I came to the United States, in India, a letter sent from one city to another would typically take 2, 3 weeks, isn't it? You send a letter from Bangalore, and by the time it reaches New Delhi, it takes a very, very long time, right? And often letters are lost and things happen. But even then, when you came to the United States in the in the 90s, you would notice that letters tend not to get lost. And there's a very interesting reason for it. This LeanNet architecture, it could do handwriting recognition. It could, you handwrite on your letter. And if you ever look at a mail envelope carefully, at the very bottom of the mail envelope, you'll see these little squiggly marks, these vertical bars, like a barcode of sorts, very tiny little markings. So what has happened is when you put your mail into the mailbox, it goes through automatic sorters. The only time a human being gets involved is the person who took all the mail, the box of mails, and dumped it into the big pile that goes to the sorter. The sorter has a neural network that recognizes your handwriting. It infers what address that you have written, and it takes the address and writes it in a digital form at the bottom of the envelope. And thereafter, the entire routing of that envelope, that letter, all the way to the destination post office happens purely automatically. It takes the best possible routes, and all these optimizations take place. No human being is involved. When it reaches the final destination, even there it is properly sorted that this belongs to the postman who addresses these streets. So the postman just gets a box of mail every morning and knows that they are meant for their street and goes and delivers it. So it brings about tremendous efficiency. Right? And the letters in the United States can still go coast to coast in 3 days, more or less, give or take a day or two. They don't take weeks. If you really ask yourself, how is that even possible? Because that much is just the transit time. The reason is all the other overhead has been removed because they have been completely automated and there are neural networks doing it. And they have been doing it for decades now. Right? So what was happening is a lot of these architectures, they were emerging through a lot of trial and effort. And the theory was sort of very nascent. And some of these researchers, in the face of the fact that everybody said that neural networks are dead or they're a useless idea, they were still persisting. Actually, the most remarkable thing with neural networks is the likes of Lee Kuan and Geoffrey Hinton, etc. They survived multiple winters of neural networks. They went through and they're stuck with the idea now for, what is it, close to 30 years? 30, 40 years, they just stuck with the idea and kept working at it. And they never gave up. And then gradually, a lot of the proper pieces began to fall in place. And all of a sudden, you could see that this thing is amazing. It really works. So that's the history of deep neural networks. If you compare it, if it's, for example, if you pick up a book of neural network in the 90s, right? I think I still have on my shelf Christopher Bishop's book on a neural network from the late 90s, I believe, or early 2000s. It is completely different from what the neural network that I'm teaching you today. Right? Today, we have a lot of things that simply were not known at that time. So you can almost say that we are learning a new subject. Does that answer you? Premji, does that answer your question?
Yeah, well, I'm actually making a little comparison in my own mind, Asif. So I did attend a course on a neural network while doing my MBA at IIM, right? IIM Calcutta was a little more into quant.
Which year was it?
96, 97, right?
Oh, I didn't realize you're so much younger than me. Okay, go ahead.
Yeah. So while doing an MBA there were professors who actually were looking at using neural networks in finance and strategy. So I did a course on neural networks. I actually trained a network to predict the credit rating of debt instruments in India, right? And I built it all on a little computer, which essentially is, I mean, I doubt how much the RAM was, probably less than 32 meg. I think those were the RAMs at that time, right? Yeah.
Early Pentiums, yes.
Yeah. But yeah, everything got done. I did make a comparison between a neural network with MDA, trying to say multiple discriminant analysis that you will do in statistics and the confusion matrices and all that. But those were very puny networks, right? And I have no understanding of all the theory that we're talking about today. Those were just packaged networks that I picked up.
That's right. So the package network is the word. So what happened is that somebody figured out that this works, and you would take that and tweak it, and you make changes to it and adapt it to your problem. Right? But if you ask the people why does it work, they would give you all sorts of hand-waving arguments.
Yep.
That's where we were in those days. Now, I don't think that we are far better. We are still in the situation that this community is, it has a problem, it has a disease. People will keep on hacking, right? And when something works, then they'll try to think up a post hoc theory to justify it, right? Now, you can say that, well, why is that wrong? From an engineering perspective, a lot of things we do is like that. We experiment, we make things work. It's a very experimental approach, or the hacker's approach. So engineers are perfectly fine with that. But if you come with a theoretical background, right, if you're a mathematician, then you pretty much barf at it. And you say, how disgusting, right? We need a proper theory, proper way to march forward. And so the theory, a lot of effort is being put into the theory, and it's gradually moving forward. This paper that we are talking about today, I would say, is in that genre, that it helps you in a proper way get, at least understand a little bit more of what is happening, right? Or why these things work, right? In a very visual way, not just some theoretical post hoc reasoning and so forth.
Mm-hmm.
So that's what we are going to do. And that's why this paper is actually quite relevant. And let's study this. So this paper, actually, I'll give you the core ideas of this paper. How many of you read through this paper? You haven't, so we'll bring it together then. Let us go through that process. See, I will use a few words of the vocabulary. Let me set it here. They will talk about the minimizers. In our language, in the language in which we are doing our code, what are these? These are our optimizers. What are some of the optimizers we are familiar with?
Asif,
I'm
seeing your camera and not the board.
Oh, goodness. I haven't shared the screen yet. Okay. Thank you for pointing that out. Let me know when you see my screen.
Yes, we can see.
So we are going to talk about this paper, Visualizing the Lost Landscape of Neural Networks. A very well quoted paper, actually. If you go to arXiv, you'll be, so the number of references are in, citations are in hundreds. So, and in the deep learning research community, that's a large number. So it's a beautiful paper in a quite literal sense. You see these beautiful visualizations that are there in this particular paper. We will try to understand. And these are not just pretty pictures, they are actually very useful, or at least I like it very much. So our goal will be the following. We will study the paper, then we will study some of the visualizations that they have created. You can sort of see how the optimization process happens. They have made some movies out of it, which are very impressive. But we'll pause those videos and discuss a little bit about what we are seeing. Then we will go to a tool. It turns out that they have created a visual tool, and we will use that visual tool to see the difference between architectures and why certain architectures work and other architectures don't work so well. Are we together? And finally, the code that they use to generate all these visualizations, it is all there in GitHub. And you can take that code, that library, and create your own visualizations as you solve your problem. Right? And so it's a very powerful thing to do, to be able to, when you solve a problem, actually show the lost surface and confirm that you truly have gotten to a good minima. It's a very powerful argument to make. And I hope that we will go that extra level and make these arguments. So that's our goal. I will state the goal again in the sidebar here. Let's put it goal. Read the paper together, see the videos, and discuss. We'll see the videos and discuss. Next, we will go and use the visualization tool, use the Viz tool. And finally, look at the library. The library part, we may not get much time to, but we'll try to do, and let's hope that we can do all of it in the space of an hour or hour and a half. So we'll start first by looking at this lovely paper. So I will just, before I go into the paper, let me set the vocabulary straight. In this paper, you use the word optimizers, minimizers. Just think of them as optimizer, right? There is a little bit of a confusing terminology they use. When you have a minima of the loss function, they often, occasionally, they will use the word, am I writing the word occasionally correctly? Occasionally, they will use just a minimizer. Well, okay, I'm misspelling it. Minimizer is the word, whereas what they really meant is the minima. I suppose they meant the minimizer around the minima. What is it showing you, or what surface it is showing you? Right? When they talk about the loss surface, what does it mean? Right? So imagine this again in the case of, if you remember regression, linear regression, it used to be beta naught, beta 1, if you remember, and then this used to be the loss surface or the error surface. Right? And what used to happen is, in the case of linear regression, it was a nice paraboloid, right? It was a nice bowl. You realize that this is a two-dimensional surface, isn't it, guys? This thing is a 2D surface in the 3D space. What are the axes of the 3D space? Beta 1, beta naught, beta 1, and some loss value. The coordinates of any point is given by some value of beta naught, beta 1, and some value of the loss. Are we together? The error. So this is a recap of the theory that we did. Now, in the deep neural network, the statement made is, this is a converse. So, okay, hang on. Let's just point out one more thing. In the case of linear regression, so in the case of linear regression, the loss surface is convex. What do we mean by that? You can see that it doesn't have the concavities, the non-convexities. It doesn't go like this. Things like that, right? So you don't see a surface like this. Things like this, right? This is not convex, not non-convex. Whereas in the case of linear regression, the loss surface is convex. It has a global minima. It has a unique global minima. Unique global minima. Now, what happens with neural networks is, and that is the crux of the reason people used to argue that it doesn't work in neural networks and deep learning. In neural nets, even with one single hidden layer, forget about talking about deep, very deep neural networks, the loss surface is non-convex. Right? What do we mean by that? Pay attention to this picture. When you look at this picture, sorry, and let me relate it again to Let's look at this picture. Do you see that it has a global minima here? This is your global minima. I'll point it out. Global. It looks like the global minima. At least maybe, right? In that region. But what about these little minimas? Like, for example, if you're sitting here, or you're sitting in this little valley, or you're sitting in this little valley, they also look like local minimas, right? There's places that have put dots. Do they look like local minimas, guys, on your screen? Are you able to see that?
Yes.
Right? Local minimas is just a fancy way of saying valleys, right? So if your loss surface is like this is a non-convex surface. Right? So inherently, non-convex surfaces can have many local minimas. Right? Now, the point that we made is that generally those local minimas in a properly done neural network, they won't harm you. With momentum, you'll get past it. Right? And you see that here. What this picture is showing you is that this is actually the picture A is without something called skip connections. It is the short circuits. If you don't put short circuits and you create a very deep neural network, let's say 50 layers deep, right? Or in this particular case, 56 layers deep, then, and there's nothing special about 56, it just is a known architecture. Imagine many, many layers, then your loss surface will look like the one on the left. But if you introduce those skip connections, if you introduce those residual short circuits, then the loss surface begins to look like this. Now, which surface looks smoother and with a very clear global minima?
The right one.
The right, isn't it? So here you can imagine that with a little bit of momentum, no matter where you start, you'll end up in the global minima, right? You can start from whatever point you like. You can take your path like this, and then after some time, you will gravitate straight to this point, down to the global minima. Right? And this in practical experience shows, see what happened is, the history is, when you talk about deep neural networks, the question is how deep. The definition of deep has been changing. The initial LeNets, I think, were 10 layers or something like that, or even 7, 8 layers. I forget what the exact number is. We'll actually cover it tomorrow, so we'll know the details. Very small, and that itself was deep enough. Then as you added more and more layers to the neural network, you began to have all sorts of problems. Like yesterday, we talked about the gradient and the vanishing gradient, isn't it? That if your activation functions are not proper, you'll have vanishing gradients. And then you have to do batch normalization. You have to do some tricks to fix it. So the idea is that when you don't bring in those bag of tricks, your loss surface looks like the left one. When you bring in the bag of tricks, it begins to look like the right one. But then you begin to get an intuition of what really is happening. If you want to ask, you can, ask this what if questions. I will take a deep neural network. I will not have short circuits, but I'll have batch normalization. Then how will the loss surface look now? How much better is it just with batch normalization? How much does a batch size affect the loss surface, the smoothness of the loss surface? How much benefit do you get from residuals versus not, short circuits versus not? Right? So you can start quantifying the value of each of them in a very visual way. You can see how much it is doing or how much it is improving your situation. Right? Likewise, weight decay and regularization. How much is the regularization doing? Now, I said that regularization has a smoothing effect, right? It prevents huge vast oscillations and so forth in the actual transfer function, in the actual function, regression function or decision boundary. But then if you see it in the loss surface also, without proper regularization, you'll have a very complex loss surface. Now the implicit statement I should make is, you don't want complex, highly non-convex loss surfaces. You want loss surface which are as smooth as possible and have as flat valley as possible. So desirable, let me again put it here. So one of our desirables is in neural nets, let's put it, where should we put it? One of the desirables is to have a nice, nice, broad, and nearly flat valley. Flat valley at the global minimum. Right? This is something that you would want. The other thing you would want is close to the global minima. You see, you don't want that. Let's look at one dimension. So suppose this is your local minima, and this is your global minima, and this. So you look at this. This is your global. Let us say global minimum. This is your local minimum. This one. Are you really? So let me say A, B, C. How persuasive or how convincing is B that it really is the solution, as opposed to, let's say, C. Let me make C a little bit deeper. Right? So B is lower than C, but how convincing is it that B is far better than C? It's a question worth asking, isn't it? It doesn't seem very impressive, but if your surface was like this, and let me make it very clear, sorry. Suppose your B was like this. Now, what do you say, guys? Does B look much more convincing?
Yes.
As a and not only that, observe a nice property. Even though the loss, I mean, I'm showing it in one dimension, and so you can imagine that there's actually a multi-dimensional surface, and so forth. But observe this part of it, a region. I'll just sort of box it in. Look at this region. Yes. Look at this region, more or less this part of the region. What happens? So from this value in the, let's say that this is some parameter, some weight parameter, Wi. We don't know which weight parameter it is. This is this direction, and this is the loss. So you realize that from this value to this value of the parameter, this loss surface looks in this region, the loss surface looks convex. Isn't it, guys? It does look convex, isn't it?
Yes.
Because it has a well-defined global minima in this boxed region. And that brings up a very interesting point. It brings up the point, and that's what this authors speak about, is that the importance of starting in the right place. What if you had some strategy that made sure that your initial weight, and so let me put that word here, importance of weight initialization. So if you initialize your weight in such a way that you end up, your starting guess is someplace close to that, you start here or you start here, what will happen? You are in a region where you're very close to the global minima, and you're looking at essentially in that space, sort of a convex surface, convex loss surface. Right? So weight minimization means what? finding the weight vector. In other words, a point in the parameter space that you are starting. Right? So you start at a good point, you're likely to converge to a global minima. You start at a wrong place, you're much more likely to get stuck at a, even with momentum, you might get stuck at a local minima somewhere else. Right? There is a greater risk for it. So what we will learn as we read this paper is that in a very visual way, you'll see what really these things mean. What does it mean visually to have the right weight initialization? What does it mean really to have batch normalization? What does it mean to have small batches? What does weight decay do? Right? What do short circuits do? And isn't it lovely that if you had a visualization tool like this, when you're designing a neural net, you can actually see what your loss surface looks like. And I can't tell you guys how useful such a tool like this is, if you could use it in your work, right? Because most of the time you're sort of guessing, what architecture do I put, isn't it? How many layers should I put and things like that? If there was a systematic way for you to get visual clues on whether you're moving in the right direction or not, and if you could just see your loss surface and say, oh, I know now why my performance sucks, why my model is doing badly. And now I know what I need to do to make the model do better. It is like, walking in the forest with the light, with the lamp in your hand. Would you agree with that, guys? So that is it. But now the fundamental question comes, and there's a lot here. The author speaks of the prior work, in fact, prior work of such people like, I think this is Bengio or some big guys. Oh, Goodfellow himself. And see, these are the big names in this field. They have done some one-dimensional versions of what these guys have done, like this kind. So something like this, the work that I'm showing you, this is close to what Goodfellow and other people have done, prior work. So they talk about prior work, and then they gradually come to their idea, which is filter-wise normalization. It's a bit technical. I won't go into that. It's not that relevant for the work that we are doing. If you read through it and would like me to explain it to you, let me know and I'll explain it to you, but it gets a little bit mathematical. But here we'll talk about this. Sharp versus flat dilemma. See, you want flat minimas, right? And when do you get flat minimas? You get it when you use certain good techniques. And if you don't use good techniques, you are in trouble. So here they are looking at what happens if you use small batches versus large batch. So it's very interesting. Remember that one of the degrees of freedom we have is small batch. Right? Batch size was one of the regularization techniques we learned just last week. Do we remember that, guys? The other one that we learned about was batch normalization. So I'll just write the word batch normalization versus large. Batch normalization. What does it mean? If you have a layer and you put a mini batch of data, this layer L-1, whatever the activations come out to be of this layer, you just standardize it, the inputs. Before you feed it to the layer L, the next layer, you normalize it. What does it mean to normalize? You take Z is equal to, so to normalize a thing is X minus mu over sigma, right? Suppose here X is the A's, whatever the output came and the input to the next layer. What do you do? What is mu here, guys? Do you remember? Is the mean of them.
There's a mean.
Standard deviation. So all you do is you take this, and so what it does is it reduces the input to be zero-centered, and most of your values will be between -3 and 3. In fact, most of your values will be between -2 and 2, right? And now you take the fact that your weights, if you make sure your weights are reasonably small, you multiply those numbers with small numbers, you still have a small z. Remember the z was the weight, inner product of weight and the input vector. In this case, the input vector is the activations coming from the previous layer, L-1. Right? So L minus 1 layer. So these activations going, you normalize that. So that is batch normalization. So what is the value of batch normalization? We'll see. And then the third thing that we do is use weight decay. And we covered weight decay. Weight decay is there's actually a little bit simpler term. I'll talk about that a little bit. But essentially, your L1, your L2 reg and L1 regularization that we learned about, regularization, are also weight decays. In fact, they're effective. They're good weight decays. What they do is they every time you take a step, like you write a loss function. If you remember, we wrote a loss function as sum squared error y hat minus y squared summed over all the i's plus lambda. You remember that weight k square, isn't it? If you solve for this, you would realize that the adjustment to the weight next, when you remember to account for this factor would be, it will basically be something like, and I might get the mathematics a little bit wrong here. So be careful. I think there's a factor of n, which is the batch size or something like that, times the number of n is the batch size. So this one, right, may be wrong. You can look it up. I'm just giving you the core idea, may be off. Times the weight minus alpha dl d weight. Right? So we always wrote it like this, weight minus alpha dl d weight. But what we are seeing is when you put a regularization term, and we never talked about the regularization term very explicitly, but when you bring it in, you realize that this equation gets modified by the fact that you first scale it down by a factor, a small factor, and then you do the gradient descent step, the next value. So what does it mean? Suppose initial weight was 1. You first start with, let's say that your lambda is 0.1. So you start with 0.9 and then you take the gradient descent step. That's why you shrink the weight first and then you take the gradient descent step. That's what it means to regularize in many ways, right? So weight decay was another technique we used. And the fourth technique, which I haven't taught you, is the so-called short circuits. Short circuit, skip connection, residual connection. These are synonyms to it. Connections. What it means roughly is, suppose you have data coming in, X here, right, for a layer LA, and then you have LB, layer B. So you would expect it to go to the next layer, right, and to the next layer. But in this, what you do is many layers later you have this. But what you do every once in a while, you take the output of an early layer and you feed it in, or maybe I'll feed it into another one here. So what you do is you will feed that also here. So that the input to this neural net will not only be from the previous layer. So suppose this is layer L, and this is layer L minus 1. Actually, let me just call this AB. A layer and B layer. First layer, second layer, let's say. And so what you would do is occasionally you would take the output of one of the early layers and add that as input to one of the later layers. So it is a form of short circuit, right? Because the normal signal is getting passed in the forward direction, and now here you have put a short circuit. So when you put a short circuit, we know that it is very essential to put short circuits, and then only can you create really deep neural networks. So today, and this work came out in the year 2014. I believe it was Microsoft. They proposed the ResNet architecture. And in the ResNet architecture, the moment they proposed them, all they did is add short circuit. Immediately, they won the ImageNet annual award, the prize. They became #1, the champions of it. If I remember right, even the second position went at that time to another research group in Microsoft. They created the VGG architecture, which we'll again talk about. These are things you'll encounter in the next week. So this is it. It's the power of those ideas. But you can put short circuits into this. One of the benefits that you have is you can create very deep.
So Asif, this is like the ResNet block are you talking about, or
This is exactly that. This is a short,
okay?
okay, a deep, very deep networks. So you can create very deep networks. Can you guess, guys, like 3-layer, 4-layer, 10-layer, how deep are we today?
Millions?
No, not millions. We haven't gone that far.
Okay.
Remember that even by the time you reach 10 layers deep, you already have millions of parameters to train,
Yeah.
right? Not just millions, tens of millions or hundreds of millions of parameters to train. Some of the largest models that I've seen have close to, they have a few
1,000,
thousand, yeah, they have a few thousand layers.
few thousand layers. Yeah, I think ResNet was the first one to go to 1,000 layers
ResNet is, no, ResNet is
initially. Yeah.
in the hundreds. The first version was 56 and then 101 or something like that.
Yeah, the 101 was the one which won the prize, like in 2004, 14. Yeah.
Okay, so that is the story for this idea of using short circuits. So now, guys, do you notice that there are 4 degrees of freedom? You can improve your neural architecture by doing any one of these 4, and the 5th thing you can do, of course, is what are the other things you can do? Play with different activations. 6, in the play with number of layers. Right? Not to mention all the hyperparameters, like how strongly you want to dampen, how much is the regularization coefficient, or what is the learning rate, and many other hyperparameters are there when you are trying to build a model, and train a model. And everything has an effect on the quality of the model that you come up with. But there has to be one way to know that you are making progress in the right direction. And usually the only way we had till now was you would just look at the training loss, right? How many mistakes you're making on the, not training loss, test loss on the test data. But when you do that, it shouldn't be just fiddling around. So suppose I tell you that your test loss is still high. You have many things you can do. You can add a few more layers. You can go change your activations. You can change some of the hyperparameters, your learning rates, your damping factors, your regularization factors. You can change your dropout. Oh, by the way, not to mention dropout. Dropout, even though it's a regularization technique, I'll explicitly mention it here. Dropout. You can change your dropouts. You can do so many things, batch normalization. Whether or not you're doing batch normalization, you can also change the size of your batch. So with all these choices, which one would you do? And you need some guide to take you forward. And in some sense, right, tools like this, no one tool will get the job done, but the tools like this, they help you. They give you some assistance. They're not perfect, but they give you some assistance. So let us learn to interpret these tools. We'll just assume that their method works. And I'll give you an idea, a rough idea, in short, how the method works. So you realize that they are in very high dimensional space, that the dimensionality of the space B, M, very high. Think hundreds, think millions. Even a standard, the very basic, I think, LeNet has 500,000 parameters and so forth. So something like that, a very high dimensionality it has. Then how do you visualize? Because when we visualize, we are limited to 3 dimensions, and loss takes 1 dimension, right? So if you do 3-dimensional visualization, you know that your vertical axis has to be the loss function, right? The loss value. So what do these 2 vectors be? What can they be? And the answer is very interesting, actually. You can take the vectors to be, let's say, Wi, Wj. Now, how do you choose these? You have millions of these to choose from. So you could choose 2 orthogonal vectors, just 2 random vectors. 2 random vectors. But actually, that doesn't help you, because if you choose two random vectors, the problem that you encounter is, suppose you have a path, a gradient descent path that goes like this, right? What will happen is these two vectors, they'll define a plane, and very likely this plane will be perpendicular to the actual gradient descent path. And so what will it look? If you look at this thing, projected it into the plane, it will look as though the point is just budged, maybe hardly even budged, isn't it? Do you see this point, guys? If this path is perpendicular to the plane, then when you look at it in the plane space, you won't see any lost surface. You'll see that the point has barely moved. It has just jiggled around. Whereas in reality, what it has done is, it was actually traversed a suboptimal, and in this paper, they use the word theta, let's say theta naught and theta 1, gone from one place to a better place. Right? So they have traversed quite a distance in the lost surface, but any two random vectors, if you take, and those random vectors happen to be perpendicular to your path, you won't see the path. You won't have any visualization. Is this idea coming across geometrically, guys? This is an important idea. So imagine a ball bounces up and comes down. If you were only looking at the shadow of the ball on the ground, what can you say?
It's perpendicular to it.
Yeah, that's right. So if the sun is shining up straight at noon up there, it's casting a shadow down, and the ball just goes up and comes down, you would hardly see the ball move. Maybe you'll see it wiggle a little bit at most. Do we agree, guys? Yeah, that is the same thing, that if this path that you take, if it happens to be perpendicular to the two random vectors that you took, the surface of the two random vectors, any two random vectors will draw out a surface, but then you won't really see a path. So now comes the bad news. It is something that mathematicians have always known. You know what? If you take any two random vectors, you are practically guaranteed that it will be orthogonal to your path. It will be perpendicular to your path, right? And the reason for that is, any two, it's a mathematical fact that any two vectors in high dimensional space, you just draw any two vectors, random vectors, and you will realize will be perpendicular. They will be orthogonal, or the word is orthogonal. Or simply put, they'll be perpendicular to each other. Right? It's a fact, and it's a very demoralizing fact that is almost always true. Right? So what do we do then? So what these guys do is something clever. They find that at this given point, you can do a principal component analysis. Do you guys remember PCA? Principal component analysis. Guys, most of you have taken ML 100, 200 with me. Please say yes.
Yes.
I hope you remember that. So what does PCA do? It finds the important features or directions, right? Uncovers the important features or directions at that point. And so what happens is, you end up picking the right two WIs, and so now you can draw your loss surface like this. This loss surface that you see here in this picture, this, sorry, let me take a different color. These loss surfaces that you see here can be drawn by taking judiciously two of those parameters, the parameter directions, right, in a careful way, and then it is it. Now you have projected down the data. What have you done? You have reduced the loss surface to a very low dimensional plane. Your loss surface was a function of W0, W1, all the way to W1 million, right? WM. And now what you have done is, you have somehow projected it down to a loss surface that belongs to WI, WJ, just two of those. So it is, of course, a different loss function because it's projected down. It's the shadow of the original loss function to this. So one of the fundamental questions that comes is, Are you sure that this preserves the property of the original high dimensional loss surface? That what you see here, do you see this point, guys? What you see here, yeah, what guarantee do we have that it reflects the true higher dimensional reality? Are we together? See, you're looking at shadows, and from the shadows you're asking, can I infer or see what is happening to the real thing that is casting shadows? So then the paper goes on to argue that actually it is true that it happens. That's the good news. So after the bad news that that we have, so this is the good news part of it. They say that yes, it is reasonable to do so, and all the properties are preserved, the properties that you care about, and there is a bit of mathematics that goes into proving it. And now let's look at some pictures and let us identify. So what we'll do is, when you look at a loss surface, see this, right? It is, you look at, if this is your loss direction, loss, and these are your things. So what are these points? These curves that you see, these are called well, physicists will call it isopotential curves or surfaces, but isoloss, similar loss, same loss. Let me just call it same loss curves in 2D in higher dimension surfaces, isn't it? And when you project these down to the ground which belongs to this Wi, Wj, what you will get here is little contour surfaces, right? And then something like this. And suppose there is a local minima here. Let me just throw in a local minima here. And so what you will start seeing is somewhere here, you will see the effect of another local minima. Right? And you will see this curve begin to bend and so forth. Are we getting an idea of what we are talking about, guys? These are called the contour surfaces. Contour lines, right? Or surfaces in higher dimension. So far, so good about the vocabulary. Right? Now, we have covered these things a few times. In fact, many, many times if you have taken the entire series of workshops with me. So this should be familiar to you, isn't it? Whenever we do gradient descent, we always come back to this picture.
Yes, sir.
Okay.
Sir, one question I wanted to ask, that you were saying earlier that when it is global minima, it has to be broad at the minima. So that part I couldn't understand, why it has to be flat and broad.
See, so here's the thing. If a minima is like this, do you really trust that this is truly a minima and not just the fact that this particular sample of data that you took happened to have this?
I see. Okay.
So how do you know that something is a truly a minima versus an artifact of the sample of data you're training with?
When it is little stable.
Yes, you want stability. So a broad minima and deep minima, both of them together gives you confidence that you're looking at the real minima.
I see. Okay.
So now let's, I'll blow up this picture. Let's blow it up even more. Is this picture looking?
Yeah, it's fine.
Right. So guys, look at this. In fact, let me bring the legends in here. Yeah, look at these legends here. What are they saying? This is, if you look at this figure, here they are saying CIFAR. CIFAR is the, did we encounter CIFAR in our lab work, guys? Our very first lab was with CIFAR data, remember?
Yeah.
Yes. So CIFAR, that is it. Now we are familiar with it. This is ResNet, this is wide ResNet on CIFAR, both with short circuit connections, stop, and without short circuit connections. So you take the wide ResNet. So wide is something interesting. What does wide means? In each layer, you have a lot more number of nodes than you would normally put. Right? When you have a lot of nodes in each layer, it is called a wide network. So given the wide network, let's start looking at it here. Yeah. And now what they are looking at is the effect of adding more filters. So that is another hyperparameter, right? Do you get better results when you put a lot of filters into your data, into your model? What filters are? We'll learn about exactly next week. But just think of it as stencils, you know, cutout stencils. One cutout stencil is for A, another cutout stencil is for B, and then you can move that stencil over a page of writing and see where it matches. Right. So if you find a match for the A stencil, you know that you've discovered an A. If you find a match for the B stencil, you say that, oh yes, there's a B here. Right. And you can use the stencil and scan over the page and count the number of A's and B's and the locations. So that is the
one quick question on the when you read it, wide ResNet 56 on CIFAR 10, what does that mean?
So what it means is this network has basically 56 layers. Sorry, this is so wide, and I'm using 56 layers. Right, literally 56 layers are there. This is number of layers. Wide just means that each layer has a lot of nodes in it, right? And ResNet was that architecture. ResNet was the famously discovered 2014 architecture that won the ImageNet contest. Are we together? Okay. And its quality is that the big idea with this ResNet was that it between the layers, it had short circuits. Right? So as the data flowed through it, it had all sorts of short circuits built in. Right? And are we together? You were literally short circuiting some of the input to the subsequent layers. So now, what happens if you go and disable the short circuits? If I take that architecture was very successful. So surely something was good about it, right? It was truly able to find good global minimas in a nice way. So if it found the global minimas in the nice way, you can see that here. If you take one filter, do you see that what can you say about the first picture, guys? Pay attention to this picture and let's talk about it. Where is the global minima? In the dead center of this picture, right? This is your global minima, right?
In the center, yeah.
Center. But observe that that is not the only minima we have. We also have another minima here, another minima here, another minima here, another minima here. Those are tiny little minimas, and most likely we can jump out of them. But that is what you get when you have ResNet with its short circuits present, but you use only one filter. Right? In a certain layer, you use only one filter. But what happens if you increase the number of filters? Do you notice that? When you increase the number of filters, close to the global minima, now how does it look? Very close to the global minima. Do you see a lot of local minimas nearby? They have decreased, isn't it? You can spot a local minima, one lurking right here, and one maybe lurking near the periphery, and one maybe somewhere here out of the region, might be one, right? But do you notice that already this global minima seems to be much more well-defined, and it seems to be a nice flat. Do you see that the contour lines are spaced apart? Observe that the contour lines, they are much more spaced apart, isn't it? When these contour lines are spaced apart, what can you conclude from this? You can conclude a wide minima. isn't it? And the fact that other minimas are far, it also means that it is a deep minima. So it's a nice wide, it's beginning to look like this, right? And it gets even better. What happens when you take k is equal to 4? You increase the number of filters in that there. And I apologize, I'm using the word filter again and again. It's something you'll learn tomorrow. So we are a bit ahead, but think of it as something, another point that improves an architecture. And one of the choices you have is how many filters. But the more the filter, it also slows down the computation, and there are aspects to it. So now what happens, guys? Does the minima get even more defined? You can't even see the local minimas anymore. They are far off. Would you agree, guys?
Yes, sir.
Yes.
It is there. And not only that, it looks like a pretty deep minima, because you can see that if you look here, right, it is pretty steep here, and then it is rather flat here, right? It's broad or flat here. And outside in the corners, if you go out, you see that it is actually both, it is actually deep. It seems to be deep. And the same process is even more exaggerated when you go to k is equal to 8. Now, there is a bit of mathematics, you know, what do we mean by flat and this and that? How do you measure the curvature, right? And this is a bit of geometry, and if you're used to principal curvatures. So in other words, if you look at my hand, the principal curvatures are, one is the curvature here, one is the curvature like this, right? The two curvature directions, orthogonal curvatures. So it might be, for example, if I have a knuckle-like behavior, do you see that it's rather steep here on your knuckle, but it would be not so steep around if you go over the knuckles. You know, if you go along this, it is not so steep, but along this, it is much more steep. Curvature is much more there along this direction than along this direction. So how do you find curvatures? There's a bit of mathematics. You can take something called the Hessian, which is a second derivative. And in multivariate calculus, it becomes a matrix. Right? When you take the Hessian of the laws and you take its eigenvalues, it turns out that that will produce for you the principal curvatures. Right? So if you're, and so here is a word to remember, that if your Hessian is generally positive, very positive, like in these situations, because I'm mentioning it because it talks about that mathematics. If it is generally positive, it is a positive curvature. If you want the intuition here, remember that in a single variate calculus also, when you have a function at this, the slope is 0, right? df dx is 0. Slope is flat. But the d square f dx square is greater than 0. It has to be. Otherwise, it is not a minima. Right? In other words, the second derivative has to be positive. And now generalize it to multivariate calculus. You have the Hessian. Because there are multiple terms in the second derivative. There will be things like d square f dx I dxj terms, right? Where xi and xj are two of the directions, two of the axes. And so what you want is that the Hessian, which is the entire matrix, that should be positive. When that, so this is just a very rough hand-waving explanation of what Hessian is. And you have positive curvatures when you have the eigenvalues and you can look at it. So there is a bit of mathematics which he talks about, but till you guys do engineering math with me, at this moment you can ignore it. There's nothing mysterious, it's a very simple idea. So this is it. As you increase the number of filters, it improves. And now let's look at the lower one. If you disable the short circuits, see what happens when you disable the short circuits. K is equal to 1. Do you notice? Compare these two. Which is better, the upper one or the lower one? Upper one.
The upper one.
Look at it. The global minima is here, but what about the local minima? What is it? It is infested with lots of local minimas around it. For example, how many local? I can see one. Oops, sorry. Here, this is the wrong color I chose. Give me a moment. Yes. Where's the black color? There it is. I could. It is just in. Oh goodness! I'm picking black and something else is coming in. Once again, It is infested with lot of local minimas. I mean, it's hard to even pinpoint. There's so many of them all around it, even here. So you can imagine that this surface is very non-convex. It's a highly non-convex surface. Would you agree? It presents this one. Oh, sorry. What is going on here? Oh, maybe it will not let me. I'll have to zoom out a little bit, guys. Otherwise, it won't let me write. So, reduce the limitation. Okay, little bit. And let's try a luck now. Yes. So this has very non-convex, highly non-convex surface, right? So here we have removed all the residuals. So this was the world before we discovered. The lower line, the lower row is the world before we discovered residuals, the value of residuals. Now you increase K, it gets better, isn't it, guys? Does it look better now? Right? It has how many local minima? Some here, 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 here. But it's not as bad, and this is your global minima here. It's not as bad as the first picture, the leftmost picture, isn't it? And as you increase the value, as you keep on increasing your K, it gets better and it gets better. But it never gets as good as the upper one. You realize that the first row counterpart of every column is much more, is far superior to the lower one. Is that clear, guys? Okay.
Yes,
And
sir.
so what you have is, isn't it very nice to see all of these things visually?
Right.
So that is the point. That's the point that they make. And then they go more into it. I want geometry after.
So what is the percentage in the figure? Is the test error? Those 10.2.
Yes, yes. Question. I don't know what it was. I forgot what they were referring to. Read the paper. You'll see what they were referring to. A test error is reported. Oh yeah, the test error. This is the amount of test error. No, but that is, yeah. So do you notice that the test error, yes, the test error is decreasing. You have 5.85, and this is a much higher test error, 13.3, right? Means 13.31% of the data you got wrong. Now, as you go here, the test error decreases as you move in this direction. It decreases as you go from left to right, and it increases as you go from top to bottom. Harini, is that, you see that, right?
Yes, sir. Thank you.
That is what they're talking about. So, all right, guys, that is how we read this paper. We move forward. Now, see, why are these surfaces bad? Or why is this bad? It has very poor ability to generalize or learn. Machine learning is all the ability to look at certain instances and generalize from that. Ultimately, this is poor results. You know, it's not generalizing. It is having a lot of test errors, high test errors. So that is it. So, and one more thing that I didn't mention is that this was for ResNet 56. You can compare ResNet 56 to 101, the other architecture with even deeper layers, and you realize that, so yeah, this is another visualization showing the same thing, that here, the the minimas are much more defined. In 56, it's just all over the place. So then forget about this optimal trajectories and so. So this was the point that I told you, that, you know, if you have a trajectory and if you're looking at orthogonal surfaces, the projections, you won't see it. That argument we made. And this is what it is. I won't go too much into that. Right? And this is the factor. This shows how much the effect is of weight decay. What is weight decay? Think of regularization. L2 is an example of weight decay. At each step, you shrink the weight. Now, you also, that more technical way would be to say that any weight in the next step is 1 minus some proportionality times the previous value of the weight, next, minus alpha d loss dw. But if you look at it, this one of the cases that produces this kind of weight decay is the L1 L2 regularization actually. L2 produces not L1, L2 will produce, L2 reg will produce weight regularization. But you can have more explicit weight regularization by just setting the weight regularization parameter explicitly. So there is a subtle difference between the two. So when you do that, if you do weight decay and don't do weight decay, right? So here you are doing weight decay, and here you're not doing weight decay. What do you notice, guys? Here is a minima, and the other, the minima is pretty sharp. You know, the other minima is lurking close by. Do you see that, guys? Right? There's another minima lurking close by. But when you have weight decay, this minima is like separated out from other minimas. Things look much better in these pictures. Right? So that is the point that when you have proper weight decay, it's a good idea, because again your loss surfaces, they look better, right? And at least locally they seem to have a nice, in a certain region close to the minima, you have a lot of, that's it, the paper is over. And so that was the paper, and our time is also over. It's 1:30. So I'll take a few questions. Guys, did you understand this paper now?
Yes, Asif.
Of what it is saying.
Nope.
Right? So now I would like to give another 10 minutes to showing you the tools and showing it to you in a very visual way. Let me go here to the share the other screen rather. PDF, OneNote. So if you go to a class page, which we should do now, this was the paper. I was trying to insert. Where am I? What just happened here? Oh, the login page itself has disappeared. Sort of log into your account. If you go into this navigation, you will see that we have in the navigation this loss function, loss and gradient descent. So do go there, guys, and when you go there, you will notice that I have put a website and GitHub visualization, the loss function viewer for various architectures. Yeah, this is the one that I want to do. Oh, thank goodness. And here we go. We are here. Let's go to this link. So let's study these architectures here. Now I know that you guys don't have may not have high resolution. Is this clear, guys? So we will pick some architecture. This is ResNet 56. Right? I'll remove this. Look at ResNet. Okay, maybe look at this. Let's take an architecture with no residual, short circuits. What do you think, guys? Does this look complicated? Right? Look at that. Now you can actually see, if you look at the bottom of it, you see that there is a global minima, but all around it there are these little local minimas that can sort of trap you. And so you would imagine that it is very hard to learn, because quite often you'll end up with a solution that is not the best solution. So look into this bowl. Right? You see all the places that you can get trapped in. Then the same architecture, suppose you do bring in the shorts. Now I'll remove this and you look at this now. What about this? Do you see how well defined the global minima is?
Yes.
How nice and broad and flat it is? So this is it, use this tool. It will give you an understanding of what really is going on with these things. You can do it with smaller articles. BGG, right? How does BGG look like if I remove this? BGG is simpler. It looks like a pretty nice plate or bowl. You might drink soup in it, I suppose. And you can play this game. Let's look at the short architecture. Do you see how complex it is, guys? And do you see this ridge? Even at the minima, it has it is sort of very thin, long minima, right? It is called an eccentric minima. It's very eccentric. The ridge, do you see this? It's almost like a canyon at the bottom. This is, if you remember, this is what we talked about. What was the other example when we used to have canyons in our loss function? Do you remember, guys, from your ML 100, 200?
Collinearity?
Yes, excellent. When you have collinearity in the data, then you have this. That's what this thing shows. Right? So you have a lot of pathologies when you do that. And the same thing now, we can now do the same architecture, but with short. And you notice that it is so much more neater. This is it, guys. And so with that, I guess I am done showing you what I wanted to show you. Next, what can I do? Here is your loss landscape. So here is a beautiful thing. If you want a more readable article describing all this instead of the paper, you can go and read this article. It's a lot more readable, right? It's idiosyncratic. It sort of talks a little bit here and there, but it gets to the same ideas. You can try to read. He takes a rather, I would say, broad strokes. He probably starts with the meaning of life, it seems. But really a good article in spite of the idiosyncratic way it starts. Very nice, and it gets the idea across. You can read that simpler article on this. And then there's a website that they have, which website again is filled with a lot of these videos. And I would encourage you to watch these videos, not just the first one. Go to the gallery and explore it, guys. It will help you develop intuition about this neural networks and their architecture. So imagine, can you imagine a loss surface like this? The pink one. And you see the effect of dropout. What does it show to you? Dropout introduces a lot of fluctuations, perturbations, and noise, isn't it? And you can literally see that. Do you see this, guys, these spiky things?
Yeah.
So all of these things, it will make it very real for you. What do these things do? What do dropouts do? Right? So please do try to observe it. And even the transformers, what exactly is the transformer doing, loss landscape in this? There are a lot of things. I like this, actually. I would definitely say that go investigate it. And then if you feel up to it, then the GitHub has the whole code of it. You can play around with the code. And they give you tools for you to generate your own visualizations. And that is that. I will bring back the controls, Control Alt Shift. Should I stop the recording now, guys?
I'd be okay with it.